Picture, the countdown hits 0. You feel this absolutely deafening roar in your chest. The ground violently shakes, and thousands of tons of metal, fuel, and human ingenuity slowly defy gravity, climbing into the sky on a literal pillar of fire. It is, without a doubt, one of the most awe-inspiring sights on Earth. But behind all that smoke, the noise, and the sheer spectacle of a rocket launch lies something incredibly elegant. It's not magic, it's math. Today, in this explainer, we're going to strip away the fire and the fury to look at the very anatomy of a launch. We're going to completely demystify the single most important mathematical formula in aerospace engineering, the rocket thrust equation.
Okay, let's dive right into this. Here is our launch sequence for today. We'll start with Section 1, the principle of thrust, move into Section 2, unlocking the thrust equation, and then Section 3, momentum and pressure explained. After that, we'll explore Section 4, sea level versus vacuum, and finally wrap up with Section 5, engineering the perfect rocket.
So, Section 1, the principle of thrust, the absolute baseline of rocket science. Let's talk about the fundamental problem here, gravity and atmospheric drag. To solve this and actually get off the ground, rockets have to expel combustion gases at extremely high velocities.
Sitting there on the launch pad, a rocket is fighting a massive battle against gravity. To win that fight, we rely on a universally understood rule, Newton's third law of motion. For every action, there's an equal and opposite reaction. Think of letting a blown-up balloon go, right? The air rushes out the back, pushing the balloon forward. Inside a rocket, it's the same idea but way more intense. High-temperature, high-pressure gases are violently expelled backward. That's your action. In response, an equal physical force pushes the rocket forward. That is your reaction. The backward-moving gas is quite literally physically pushing the rocket in the opposite direction.
And this brilliantly illustrates the violent, brilliant chain reaction happening inside the engine where fuel is converted into upward motion. It's a total masterclass in energy conversion. First, fuel and oxidizer are pumped into the combustion chamber. This triggers a chemical combustion, releasing a massive amount of thermal energy, which creates highly compressed gases. Then, these gases expand rapidly through a specially shaped nozzle, converting that pressure into pure kinetic energy as the exhaust leaves at extreme speeds. The final result of this five-step sequence? Thrust. We've literally turned chemical potential into pure upward motion.
Section 2. Unlocking the thrust equation, the math behind the machine. This is where we introduce our main character, derived straight from the principle of conservation of linear momentum.
Now that we understand the physical principle, let's look at the actual formula. Engineers predict a rocket's power using this equation, allowing them to calculate exactly what an engine will do before it ever leaves the drafting board. Here it is in its most distilled form. Total thrust, represented by the letter F, is equal to momentum thrust plus pressure thrust. This tells us something absolutely crucial. The total propulsive force isn't just one single action. It is a combination of two distinct and honestly sometimes competing halves that we are going to deconstruct right now.
Section 3, momentum and pressure explained. Let's transition into breaking this equation down, separating the internal and external forces. We need to look at what the rocket generates internally versus the external environment it's flying through.
Let's translate these mathematical variables into physical realities, shall we? On one side, we have momentum thrust. This is driven by the mass flow rate, which is just the sheer volume of fuel violently spit out every single second, multiplied by its exhaust velocity. Just to put that into perspective, the Saturn V rocket burned through roughly 13 tons of fuel per second. Now, on the other side is pressure thrust. This is kind of the wild card. It entirely depends on the external environment, specifically the difference between the gas pressure exiting the nozzle and the ambient atmospheric pressure pushing back from the outside at that exact moment in flight.
Now, what's really interesting about this slide is the sheer imbalance between these two forces. Looking at the data for a typical modern rocket engine, momentum thrust does the vast majority of the heavy lifting. We're talking anywhere from 90 to 98% of the total thrust. Pumping out more fuel faster is your direct path to power. Pressure thrust is just a small slice of the pie here, but it plays a critical and super volatile role.
Let's look a little closer at that pressure thrust, because its behavior completely changes depending on where the rocket actually is. The equation relies on the difference between exit pressure, which we call P, and ambient pressure, P. If the exit pressure is greater than the surrounding atmosphere, pressure thrust is positive. It helps the rocket. If they are exactly equal, pressure thrust is 0, meaning you have a perfectly expanded nozzle. But here's the catch. If the ambient atmosphere is pushing back harder than the exhaust pressure, your pressure thrust actually becomes negative.
The atmosphere physically suppresses the exhaust, completely reducing your total thrust.
Section 4. Sea level versus vacuum, the atmospheric battle. Get ready for a bit of a plot twist here, because the environment drastically changes a rocket's performance as it ascends.
A rocket doesn't just sit on the ground, right? It climbs. And as it goes up, the environment changes drastically. Down at sea level, the atmosphere is incredibly heavy, about 101.3 kilopascals pressing in on the engine. This high ambient pressure pushes back and suppresses the exhaust, resulting in a lower pressure thrust component, which means lower total thrust. But in the vacuum of space, ambient pressure is essentially zero. There is literally nothing pushing back against the nozzle exit. This reveals a highly counterintuitive truth. Rocket engines actually perform better and produce more thrust in the empty vacuum of space than they do sitting right there on the launch pad.
Let's move to and see how this builds into Section 5, Engineering the Perfect Rocket. We're going to zoom out from the formula to see how engineers manipulate these exact variables to build spacecraft.
How do engineers actually take these exact variables and build spacecraft that reliably carry payloads and humans into orbit? Well, to maximize that thrust equation, it's a massive, incredibly complex engineering balancing act. You need to maximize the propellant mass flow rate, meaning you have to pump that fuel insanely fast. You need to increase exhaust velocity. You want to crank up the chamber pressure to get better nozzle expansion. And you have to perfectly calculate the nozzle exit area to match the changing ambient conditions as you climb. It's fluid thermodynamics on a monumental scale.
So the crucial point is this. You can't just maximize performance blindly. Pushing chamber pressures and exhaust velocities to their absolute limits creates astronomical thermal and mechanical stress on the vehicle. Engine design must ensure high combustion efficiency without the flame becoming unstable. They have to minimize pressure losses, all while guaranteeing the structural integrity of the vehicle under extreme loads. Because look, if you maximize thrust but your engine melts or shatters under the pressure, you don't go to space, you just have a really expensive explosion. Balancing that high performance with rigorous safety is the true art of rocket science.
Which leaves us looking toward the horizon. The thrust equation is already taking humanity to the moon, and it's currently landing reusable rockets perfectly back on robotic ships at sea. But as we push even further into the cosmos, looking toward Mars, advanced planetary landers, and heavy-lift reusable architectures, how will our evolving mastery of this fundamental equation shape the entire future of deep space exploration? Every new engine, every new nozzle design is just another brilliant attempt to perfect these very same variables. Thank you so much for joining me on this explainer, and keep looking up.